Hello everyone, my name is Eric Turman. I'm a master's student at Liberty University studying under Dr. Wayne Strasser, and today I will be discussing my comparison study of the shear stress transport and the differential Reynolds stress model for predicting flow currents and heat generation within an LDPE autoclave reactor. We developed a CFD model of this low-density polyethylene autoclave reactor to study heat generation throughout and the effect of polymerization taking place at different points in this model. So it has a centralized stirring shaft that runs the entire length with zone baffles separating the reactor into 4 separate zones. The operating temperatures can be between 200 and 300 degrees Celsius, with operating pressures between 100 and 3,500 atmospheres. The rotational Reynolds number is around 25,000 in the bulk flow regions, and I will note that we have automated controllers to control the temperature at different points within the reactor. Now, the overall purpose of this study was to look at heat generation and to predict where thermal runaway could occur within the reactor. We have reaction kinetics included, which are highly exothermic in nature. So as we have more reactions taking place, there's more heat being generated. And if we get to a point where there's too much heat, we enter thermal runaway where the reactor cannot be handled anymore and can potentially explode, which is not desirable. So we're using CFD to predict the locations and conditions of hotspots with the potential for thermal runaway. And part of this study was to look at the sensitivity that this has to turbulence model, hence the work I'm presenting here. Diving into model setup, we'll start with the grid development. We used 5.7 million computational elements to represent the entire reactor. Most of these were hexagonal, but we also had to use polyhedral elements where structured meshing became difficult. We had a multi-tiered rotating zone to encapsulate the stirring shaft, which had various protrusions and irregular shapes that in the actual reactor induced mixing, and so we had to include those within our model. Elements within the bulk flow away from the wall are around 10 to the negative 6 cubic inches, and as I mentioned, we tried to do structured mesh as much as we possibly could, but mostly around injectors and thermocouples. This became a challenge and not necessarily realistic, and so we had to use some polyhedral elements. We kept a fine mesh around the thermocouple and the injector to model any near wall effects that these would have on the bulk flow. The RANS momentum, energy, and species equations were solved. We used ANSYS 2021, segregated incompressible double precision solver. We only used a single phase consisting of 3 species, that being the initiator, monomer, and polymer, and we have boundary conditions which we cannot disclose at the request of our sponsor. Now, within the reactor, we have multiple mixing geometries and flow currents being generated to ensure the most conversion of monomer to polymer. So all the way to the left, we have this stirring shaft with multiple baffles and paddles that impact the currents and create different flow structures. We have wall baffles along the edge of the reactor wall that can create flow separation and induce mixing in different stagnant regions. And then there's also these things called gear points that invert axial flow. So if you see there's flow coming down the wall and then flow coming up the wall, meeting at a gear point where they invert each other. And so all of these need to be handled by a complex turbulence model because we need to be able to model these bulk flow effects, near wall effects, highly rotational flow, and regions with high velocity gradients. The two turbulence approaches for this study were using the shear stress transport, or SST, and the differential Reynolds stress model, DRSM, which we selected the omega-based option within ANSYS Fluent. Now, it's important to note both of these are RANS models, or Reynolds average Navier-Stokes models, which are not showing true turbulence, but just predicting the effect of turbulence. And so the SST applies a blending function to use k omega near the wall and k epsilon for the bulk flow, as both have strengths in those regions and weakness in the other. It is well calibrated for attached flows, as most linear eddy viscosity models are. It struggles with streamline curvature, turbulence, anisotropy, rapid changes in strain rate. Now, the differential Reynolds stress model, or DRSM, has an individual transport equation for each Reynolds stress. It's difficult to calibrate these higher order terms, and there's less effort done on this compared to the SST, but it does have the potential to handle highly rotational flow with high strain rates. So the first metric we're going to look at is the deviation and temperature at each thermocouple throughout the reactor compared to what we're seeing in the plant. So the deviation being the average temperature from a 60-point moving average over 10 seconds of CFD flow time minus the average temperature in the plant. So if it matches exactly what's seen in the plant, it would be at 0, which you can see occurs where we have these vertical black lines. And those are just denoting where we have controllers that are actually driving the temperatures at these thermocouples down to 0 error or 0 deviation. And so at the uncontrolled points, namely TC 2, 3, and 11, we see that the DRSM model is predicting hotter temperatures than the SST. At 7 and 8, there's a slight decrease in temperature for the DRSM, but that's negligible compared to especially looking at TC2 and TC3, which show a large jump. And so these hotter temperatures are saying that the SST model is more diffusive or reporting lower temperatures, which is something very important to our study when we're considering heat generation of this reactor. Here we see a rotating view of the shaft in zone 1 of our reactor. You can see there blue pockets of material coming in through one of the injectors, and in the SST that stays mostly around the reactor wall and doesn't penetrate in the shaft region. If you look at the DRSM model, you see these colder materials start to dissipate from the bulk flow around the wall and actually enter into the shaft region. There's these smaller structures that are penetrating into this region, unlike the SST predicts. Now I will note that the animations are made with different frame rates, but the shaft is rotating at the same constant velocity. We have all the same boundary conditions for both of these. So this is just an effect of how we have these videos laid out. But these colder currents show that SST has greater dissipation for the velocity field and smooths out this velocity field, suppressing fluctuations. Now, DRSM computes the individual stresses and therefore can account for history effects because it's tracking each individual stress for each timestamp at each cell. And so keeping those history effects, we see that there's some momentum that transfers some of these currents into the shaft region. Now we're going to look at some of the mixing geometries that we have down in zone 3, namely the wall baffles. So as the flow encounters the wall baffle, it increases the shear in this region, which increases the instabilities, and that is increasing the turbulent kinetic energy, or K. And so as I have marked out at top, this production is taking energy from the mean flow and placing it into these fluctuations. And in the SST model, this is handled via the transport equations. Meanwhile, the Reynolds stress model is actually tracking each individual Reynolds stress and taking 1/2 the trace of those. So for the SST, we're treating these eddy fluctuations only like a scalar rather than actually calculating the true stress values and seeing how these shear are actually impacting the normal stresses. And so that SST approach of treating these eddy fluctuations as a scalar ignores explicit structure correlations involved in the production of K, while we're able to actually track the individual stresses and have the correlation interactions impact this turbulent kinetic energy within the zone using the RSM model. Now looking at turbulent viscosity ratio, or TVR, we see that again SST predicts a higher turbulent quantity than the DRSM model. Now the molecular viscosity is the same for both of these, and we're only looking at changes in nu T. So for the SST model, we have C mu, which is a constant at around 0.9, times K squared over epsilon. And K and epsilon are computed using transport equations, as I said before. Now in DRSM, we have this new variable A star, which is a function of Reynolds number, and this damps out turbulent viscosity and provides low Reynolds number corrections around the wall. Now this does have a small effect in our reactor study, as there's not a lot of near wall effects, as we see most of the red is in the bulk flow area. And I will note that alpha star goes to 1 for high Reynolds numbers. But you can see that with calculating each Reynolds stress, we're actually predicting a lower turbulent viscosity ratio for K, impacting the overall flow treatment of the reactor. Now, to summarize our results, the SST model is shown to be more diffusive. We predict a higher turbulent kinetic energy throughout the reactor, which leads to greater mixing, and that leads to more heat dissipation. We also saw large-scale fluctuations being dissipated in that contour, showing small colder structures impacting the shaft region for the DRSM, where these were not seen at all with the SST model. We also predicted a higher turbulent viscosity, backing up that there was a greater K generation throughout the reactor. DRSM was a hotter prediction for the reactor, as we showed in the temperature plot before, and it shows a better representation of K due to tracking it using tensorial stresses. But DRSM also allows us to include history effects showing those different flow correlations, and I will note that from a computational cost standpoint, a DRSM was only 13% more expensive to run on this model. So final conclusions for this study was that the flow has a very high Reynolds number, very high rotational currents, and high velocity gradients and strain rates. The SST is well calibrated for simple problems, but not necessarily complex industrial reactor problems. Numerical diffusion is bad for studying these heat-sensitive problems because we don't want to tell the plant that a certain set of boundary conditions are okay. We want to predict the hottest possible situation in CFD to avoid any thermal runaway states. So that for this complex problem, we should rely on the DRSM to better predict flow conditions and heat generation. Are there any questions? Please let me know. My email is emturman@liberty.edu. Thank you for your time.